Welcome to The Explainer. Today, we're doing something pretty amazing. We are going to decode the secret language of the entire universe. Yeah, you heard that right. We're going to find out how scientists can read these tiny messages written in light to figure out what everything is made of, from stars billions of miles away to the very molecules inside our own bodies. So let's just dive right in.
All right, so let's just jump in with a huge question. Think about it. You look up at the night sky, you see all those stars. How in the world do we know what they're made of? I mean, they're millions, sometimes billions of miles away. It's not like we can just go grab a sample, right? It honestly seems kind of impossible.
Well, the answer is surprisingly simple, but also really profound. It's light. That's it. Every single photon of light that travels across the cosmos is carrying a secret code, like a little message in a bottle, sent straight from whatever made it. So, the big question is, how do we crack that code? Well, in this first part, we're going to uncover the invisible secrets that are hidden inside every single beam of light, and we're going to learn how to actually read the stories they're telling us.
Okay, so the tool that lets us do this is called spectroscopy. That might sound complicated, but the idea is actually pretty straightforward. It's just the study of how electromagnetic radiation, and that's just a fancy term for everything from radio waves to gamma rays, and yeah, the visible light we see every day, how all that stuff interacts with matter. And believe me, that interaction, that's the key. That's how we unlock what pretty much anything is made of.
So this diagram here really breaks it down for us. It's pretty simple. Over on the left, you've got an emitter. Think of a star or a light bulb, and it's sending out all the colors, the whole rainbow of radiation. Then that light passes through a sample. Let's imagine it's a cloud of gas out in space. Now as the light goes through, the atoms in that gas get a little picky. They absorb very specific colors of light, like they're grabbing their favorite snacks. So what comes out on the other side? It's a spectrum, but with little black lines, missing pieces. A machine called a spectrometer reads that, and those missing pieces, they're like a barcode. A unique barcode that tells us exactly what that gas is made of. It's amazing.
Okay, so to read that light barcode, we're going to need a map. And that map is the electromagnetic spectrum. And here it is in all its glory. The electromagnetic spectrum is this gigantic range of energy. I mean, it's huge. Way over on one side, you have these super low energy radio waves. Then as you move across, the energy ramps up and up until you get to the other side with these incredibly high energy gamma rays. And the funny thing is, visible light, everything we can see with our eyes, it's just this tiny, tiny little slice right in the middle. But here's the most important part. Different bits of this spectrum make matter do very different things.
So how exactly does matter react to all this energy? Well, a molecule isn't just a boring, static ball. No way. It's constantly moving. It can zip through space, right? It can also spin around like a top. That's rotation. And the bonds holding it together, they can stretch and bend like tiny little springs. We call that vibration. Oh, and its electrons can hold energy too. So here's the kicker. Each type of radiation on our map targets one of these specific motions.
And there's a really clear order to this, a kind of energy hierarchy. Think of it like this. It only takes a little bit of energy to get a molecule to spin. It takes a bit more energy to get its bonds to vibrate, and it takes the most energy out of all of these to actually kick one of its electrons into a higher energy level. This one simple rule is basically the foundation for everything else we're about to talk about. It's super important.
All right, let's start at the low energy end of our map. In this next part, we're going to see how we can literally make molecules dance.
First up, microwaves. And yep, we're talking about the same kind of waves that are in your kitchen oven. But in the lab, or out in space, scientists use them because they have just the right amount of energy to make certain molecules start to spin. It doesn't break them or anything, it just gets them tumbling around. And that's actually how radio astronomers can spot different molecules rotating way out in deep space.
Okay, let's climb up that energy ladder a bit to infrared radiation. Now this is really cool. Infrared light doesn't make the whole molecule spin around. Instead, it targets the individual bonds inside the molecule and makes them vibrate. Seriously, just picture tiny little springs connecting all the atoms, and the infrared light makes them stretch and bend. And here's the secret sauce. Different bonds, like a carbon to oxygen bond compared to a carbon to hydrogen bond, they all vibrate at their own unique frequency. They will only absorb the exact frequency of infrared light that matches their own personal rhythm.
And this is what we get as a result. This is an IR spectrum. At first, it just looks like a bunch of spiky dips on a graph, right? But each one of those dips tells us something incredibly specific. It shows us that a certain frequency of light was absorbed, which means a certain type of bond is wiggling around in there. We can even break it down. The left side tells us about the key building blocks of the molecule, but the right side, that's the fingerprint region. It's totally unique to that one specific molecule. It is, quite literally, a molecular fingerprint.
Okay, so we've made molecules spin, and we've made them vibrate. Now let's crank up the energy. We're going to see what happens when we get into the realm of visible and ultraviolet light. And this is where things get really interesting. We're about to take a quantum leap.
So with this much more powerful light, like UV or visible light, we're not just shaking the molecule anymore. We're actually giving enough energy to an electron to kick it from its cozy home, its ground state, all the way up to a higher, excited state. That's absorption. The light gets soaked up. But here's the thing. That excited state is super unstable. The electron can't stay there for long, so it falls back down, and when it does, it releases that extra energy as a brand new photon of light. That's called emission. And we can study either one, the light that gets absorbed or the light that gets spit back out, and both of them tell us a totally unique story.
Probably the best way to think about this is with the ladder analogy you see here. Imagine an electron's energy levels are the rungs of a ladder. An electron can't just hang out in the space between the rungs, right? It has to be on one or the other. And to jump from a lower rung to a higher one, it needs the perfect amount of energy from a photon of light. Not too much, not too little, the exact amount. Any other amount of energy just won't work. And that is the core reason why any substance only absorbs very specific colors of light.
Okay, deep breath. We've seen molecules spin, we've seen them vibrate, and now we've seen their electrons do these incredible jumps. So let's pull all of this together and look at the big picture. How we decode these unique molecular fingerprints.
You know, this table right here is the perfect summary of our whole journey. At the super low energy end, you have radio waves, which are used in things like MRI. Then come microwaves, which make molecules rotate. A little more energy, you get infrared, which makes them vibrate. And then you hit the UV and visible light, which gives electrons that big kick they need to jump energy levels. You see? Each type of radiation is just a different tool in the toolbox for asking a different question about the molecule.
And this quote really nails why all this is so important. It says, by studying the absorption pattern, scientists can gain insights into the composition, structure, and concentration of the substance being analyzed. So what does that really mean? It means it's not just about figuring out what something is. It's about understanding how it's built, its structure, and even how much of it is there. Whether you're trying to figure out what a planet's atmosphere is made of or you're just checking if a medicine is pure, this is the exact technique scientists use.
So when you boil it all down, here's the big takeaway. Every single thing in the universe, every atom, every star is constantly telling its own story. And that story is written in the language of light. With this amazing tool, spectroscopy, we finally figured out how to read it. And that just leaves us with one final, kind of mind-blowing thought. What other stories are still out there, written in light, just waiting for us to read them?